In this capstone, you'll bring the full workflow together: credentials, wallets, verifiers, zero-knowledge proofs, and a protected resource. The practical goal is to design, build, test, and demo an access control application that proves eligibility without exposing unnecessary personal data. By this point, you have the full toolkit: identity foundations, cryptography, credential issuance, wallet flows, verification, and privacy-preserving disclosure. The capstone connects those pieces into one production-minded ZKP flow while keeping security, trust decisions, and implementation trade-offs in view. At the center of the capstone is a simple idea: access is driven by proof, not by exposing personal data. A user holds a verifiable credential, such as proof of age or membership. When they request a protected resource, the application asks only for the facts required by policy. The user generates a zero-knowledge or selective disclosure proof, and the verifier checks it against the rules. If the proof is valid, access is granted without sharing the underlying credential details. Choose a scenario that is small enough to build completely, but still shows real privacy value. Age checks work well because the proof is straightforward: over a threshold, not a birth date. Membership, employee access, and event entry can also work, as long as the assumptions are clear: who issues the credential, what the verifier accepts, and how easily the demo communicates the value. Functional requirements turn the capstone into testable behavior. The issuer creates credentials with the claims the use case needs. The holder receives them, stores them safely, and generates a proof when asked. The verifier requests the proof, validates it cryptographically, and interprets the result. Finally, the protected resource uses that decision to grant, deny, or limit access. Together, these become your acceptance criteria for implementation and testing. Functional requirements define what the system does. Non-functional requirements define whether it can be trusted in real use. For VC and ZKP solutions, that includes privacy through minimal disclosure, security through checks for signatures, revocation, proof integrity and replay risk, performance that keeps proof steps fast enough for the user journey, and maintainability through documented schemas, policies, and assumptions. Treat each one as measurable. Define the target, how you will test it, and the risk if it fails. The capstone works best when each trust domain has a clear job. The issuer defines schemas, applies issuance policy, and signs credentials. The holder's wallet stores those credentials and later creates a selective disclosure or zero-knowledge proof. The verifier checks the proof, confirms that the issuer is trusted, and evaluates policy. Only then does the protected resource grant access. This separation keeps boundaries explicit and makes each lifecycle step easier to test. Strong cryptography does not make a credential system automatically trustworthy. Trust comes from a documented trust model. Define which issuers count, how their identifiers and keys are resolved, and who can revoke or update that trust. Then define holder duties, such as protecting private keys, wallets, and credential storage. Verifiers also need assumptions for freshness, challenges, and replay prevention. Finally, include infrastructure in the boundary. APIs, cores, secrets, and TLS can all affect the model. Schema design starts with the access decision you need to support. If the policy only asks whether someone is over 18, store an age over 18 claim, not a full birth date. The same principle applies to membership status, role, clearance, and expiration. Clear claim names and stable schema versions make credentials easier to verify later. And for zero-knowledge proofs, the schema must align with what the proof system can selectively reveal or prove. Issuance begins by confirming the applicant and the source data you trust. Then transform that data into credential claims using your chosen schema, format, issuer DID, and key. Next, sign the credential with the configured proof method, so verifiers can check integrity later. Delivery should happen through a secure endpoint, such as post/credentials/issue or through a wallet flow. Log only operational facts, not personal data or full credential contents. For the holder experience, the goal is trust and control. A demo might use a browser wallet or simple holder service with clear caveats about backend storage. In production, use encrypted local storage, secure enclave patterns, and strong key protection. Users should be able to see what they hold and what they are about to share. Whenever possible, generate selective disclosure or ZKP proofs instead of sending raw credentials, so verification reveals only what is required. Verification starts with the verifier asking for exactly the evidence it needs, plus a fresh challenge or nonce. That challenge helps prevent an old presentation from being replayed. The holder creates a privacy-preserving proof, revealing only required attributes or predicates. The verifier checks the cryptography, issuer trust, schema, expiration, revocation, and domain binding. Only after those checks does policy logic translate the verified claims into a concrete result, an access token, limited access, or denial. A protected resource should not make decisions from a raw proof submitted by the user. First, a verifier checks the cryptography and outputs trusted claims, predicates, or a short-lived token. Then the application maps that verified context into permissions. Age over 21 can unlock content. Employee in engineering can open an internal tool. If verification fails, deny safely with clear messaging, but without revealing policy details or sensitive data. A strong capstone needs more than a happy path demo. Test the full behavior. Valid credentials, invalid signatures, expired or revoked credentials, replay attempts, and wrong issuers. Measure what users will feel, including proof generation time, verification latency, and completion time. Then prepare a clean demo script from issuance to access decision, and document privacy guarantees, threat assumptions, limitations, and hardening steps. You now have the full pattern. Define a narrow use case, issue credentials, disclose only what is needed, verify proofs rigorously, and protect access decisions. From here, the focus shifts to production readiness, stronger keys, interoperability testing, monitoring, governance, privacy review, and a deployment plan grounded in real users and real risks.